For exponential functions, we are dealing with things of form f of x equals b raised to the power x, where we call b the base and x is an exponent. So something that's very important to understand here, something that's very important to know here, is that when we're dealing with these exponential functions, things like b raised to the power x are not equal to things like x raised to the power b. That is, exponentials and polynomials are fairly different things where over time exponentials tend to be considerably larger than polynomials. And if you want to understand what a exponential is, what it acts like, you can think of the base as defining something like a constant growth rate, and the value x there, sometimes we'll write it with a t instead, as being something like an amount of time. So this whole thing tells us a bit about how much of an object, a thing, an organism we might have after a certain amount of time, given that its growth follows a consistent multiplicative pattern. But it's a whole lot of numbers, whole lot of letters in here. It's not a whole lot of clarity just looking at those things. So let's take a classic example to appreciate the difference between exponentials and polynomial type things. What we're going to do is suppose that you win a lottery. And the terms of the lottery are that when you win, you can either take $1 million the day of, and that's your money, or you can accept a different offer to get 1 penny, where the 1 penny is a little bit magical in that at the end of every day, its value doubles. And thinking about this initially, you might say to yourself, well, this feels like some kind of mystery box bullshit.
A mystery box could be anything. It could even be a boat. You know how much we've wanted one of those.
Why would I want the 1 penny? The $1 million is $1 million, and you should just take the $1 million. But this is a math class. Let's actually do the math and see if we can actually figure out which of those deals is the better one. So, to get a little bit more context, a little bit more of the juices flowing for how this one works, by the end of the first day, the $1 million would still be the $1 million. Well,
it's 600 grand by the time Obama takes it.
At least up to taxes, but that's a different concern for a different class. Meanwhile, your penny, your magic penny here, would now be worth 2 pennies. It's a real conversation now, isn't it? And then by the second day, $1 million is still $1 million, but you'd have 4 pennies. It's getting tougher. Probably not, but if we want to actually describe what's going on, if we want to be a little bit more mathematical about it, we could say that we have 2 functions to describe the value of your lottery winnings. We have the function f1 of x is just 100 million pennies, where I'm putting it in terms of pennies rather than dollars to even out the units a little bit, so I have to deal with other like conversion factors in there and some subtlety about how those things come together. I'm just going to say it's 100 million pennies because that's what $1 million is. Meanwhile, f2 is your amount of pennies following the doubling magic penny. So it's 2 raised to the power x, because you start out with just the 1 penny, by the end of the day you have 2, then 4, then 8, 16, and so on, where it's not very impressive initially, but with this sort of scenario, we have 2 questions that we really need to ask ourselves here. One, when do these 2 things even out? When does the number of pennies you have that doubles get up to 100 million? And 2, what's the value of this thing after a month in particular? That is, how long, x, does it take for the growth rate here, b, to match up with 100 million? And is that value going to be less than 30? Because if it is, you'll have more pennies by the end of that month. You might be able to Scrooge McDuck your way through an entire pool of them if you're really lucky. I don't know, maybe you don't want to do that because it's a lot of copper, and copper is a very hard surface to swim through. But anyway, those are the types of things we need to think about here. Those are things we need to think about if we're really going to do it mathematically. Where if you do that, you see about graphing those 2 functions next to each other, you're going to see that they actually do even out. And in particular, if we look at that second one and we take that value at 30, what we would end up getting there is 1.073 with 741,834. I didn't want to say all those decimals. I should have thought that through. I don't want to be dramatic, but the point is here, we'd have over 1 billion pennies, which is more than 10 times as much as the single drawn value. That is to say, by the end of the month, the doubling scheme would work a lot better for you. Where you've probably heard this scheme somewhere else, just you might have heard this scheme somewhere else in the context of some grains of rice, a chessboard, and a very upset Chinese emperor. If you haven't, that's okay. The point here is to understand that when we're looking at these exponential functions, we're talking in terms of growths of things over time, where it might start out a little bit slow. It might not look very impressive initially, but these things really do tend to get incredibly large and do so incredibly quickly after that slow start. Where another example for how this works you can think about in everyday life is things like Moore's Law, which say that the pattern for computer storage memory and processing speed, those things tend to follow exponential type models. And because they follow exponential type models, people like Ray Kurzweil, American inventor and futurist, think that
by 2020 we'll have computers that are powerful enough to simulate the human brain, but we won't be finished yet with reverse engineering the human brain and understanding its methods. By 2029 we'll have reverse engineered and modeled and simulated all the regions of the brain, and that will provide us the software, algorithmic methods to simulate, all of the human brain's capabilities, including our emotional intelligence. By 2045, we'll have expanded the intelligence of our human-machine civilization 1 billion-fold. That will be a singularity. We borrowed this metaphor from physics to talk about an event horizon that's hard to see beyond.
Which is a terrifying prospect that also illustrates just how quickly these types of things grow and build. And to see that a little bit better, we're going to take another applied example here.